Great. Number 1.
We did number 1 in class.
Oh, we did number 1 already. Great. Okay. So then, we have number 1 done. Can you give me the answer that we got for it, so I can just write it here for the people who need to get the answer?
No, part 1 is 4.49 megajoules.
Yeah, and then part 2, the time.
In 1 minute.
It was nearly 30 minutes, wasn't it?
1,796 seconds.
Yeah, so that is nearly 30 minutes, half an hour. Okay, so that's number 1 done already. Number 2. You have an electric kettle, 1.4 kilograms of water at 20. The heat capacity is 4,200. The latent heat of vaporization is 2.3 megajoules. How much heat energy to raise the temperature to 100? Okay, so the first step is 20 degrees to 100 degrees, and the energy here is mc delta T. Will I open up the program, or just... Well, maybe someone can just hand me a calculator.
470,400.
Yeah, well, I'll take a calculator too. 470,400. Okay, thank you. Right, so that's part 1 done. Part 2 is how much further heat do you need to boil off? That means change into steam. 0.2 kilograms. So that is ml, which is 0.2 times 2.3 times 10 to the 6.
460.
Yeah, it's 0.46 times 10 to the 6 joules.
160 kilojoules.
Yes, yeah. Right, part B is how long it would take to do this part. They want to know the time for this part, the first part. So now B, part 1. Well, we know the formula. Time equals power over work, is it? Work over power. So here it's 470,400 over, what is it?
You have to add both of them together.
Well, I don't think so, because it says calculate how long it will take to heat the water to 100 degrees, not to heat the water to 100 degrees and boil off some of the water. See, I think they're trying to, not trick you, but it's an easy, I imagine a lot of people added the two together. Power is 2.5 times 10 to the 3, and let's type that in. 470,400 divided by... it is 188 seconds, about 3 minutes. 3 minutes, 8 seconds to do. And then the next part is how long would it take if it was 60% efficient. So in part 2 here, the efficiency is 60%. So you have your kettle, and the power in is 2.5 kilowatts, but the power out is not 2.5 kilowatts. It's only 60% efficient. So if we just do our 2.5 times 60%, we get only 1.5 now. So now the power is only 1.5 kilowatts. So it's the exact same, except we change this number to 1.5 instead of 2.5. So if I just go back on my calculator and change that 2.5 to 1.5, oh, right. Change that to 1.5. 313.6. So it takes nearly twice as long, isn't it? It'll take 5 minutes and how many seconds? 13 seconds to do it now. Okay, so that's part 2 done. No problem. Part Question 3 is interesting. Can I go down? Yeah. So, question 3. Liquid nitrogen. You've all seen this before. Hey Joshua, come on. Did you see Sylvia?
Yeah.
Good. Liquid nitrogen. Come on, hurry up, Joshua. Leave him alone. He'll tell you after class. Right. Now, liquid nitrogen. You've all seen this maybe on TV or science shows. It's the really, really cold liquid that people pour onto things to freeze them quickly. Huh? Yes. What's the one? I see people like putting a banana in liquid nitrogen and then hammering a nail with the banana because it's frozen solid. Have you seen this one? Yes, some people have. Anyway, liquid nitrogen, really cold. You see here, minus 196. So what we've got, an open container, and let's see, the mass of the container is 1.4 kilograms, and it's initially at 20 Celsius. Determine the mass of nitrogen which will be boiled off when the containers cool down to the temperature of the liquid nitrogen. All other sources of heat gain or loss can be ignored. Liquid nitrogen at its boiling temperature of minus 196 is poured into an open glass container. Right, so it might be difficult to understand, but this is what's happening here. Look, please. You have liquid nitrogen, liquid. So you have this liquid poured in. Its temperature is minus 196 Celsius. Okay? This is also the temperature it boils at. So this means that if it gets more heat energy, it will change, it will not increase its temperature, it will change from liquid then to gas. Okay? So it's at minus 196. This is like when water is at 100 degrees. If water is at 100 degrees and you give it more energy, what happens? It doesn't go to 101, it changes into steam. Then it goes to 101. Yes? So the question is, how much steam is made? So we're looking for the mass of the steam. Okay? Now, is it gaining or losing energy, the liquid nitrogen? Yeah, so the liquid nitrogen, I'll just write N here, that's gaining energy. And so therefore, what is losing energy here? The carbon, yeah. The copper is losing energy. And we think the two should be equal. Yes? Are you okay, Joshua? You look very unsettled. Maybe you should open up, your notebook perhaps? Just an idea. Okay. Now, what formula should I use for this one here? Should I use MC delta T or should I use ML? Soon. Problem? No. What's Donna? What formula should I use here? MC delta T or ML? Are you even listening to me? Thank you. ML. And then what formula should I use here for the copper can? Thank you. MC delta T. Alright. We don't know the M here. We do know the L. It is 199 kilo. We do know the M here. We do know the C. It's not copper, it's glass. We do know the C here is 0.75 kilo. Now, what's the delta T? What's the temperature of the copper at the start? Glass. What's the temperature of the glass at the start? 20. And what's it at the end? Minus 196 after you pour it in. So it goes from 20 to minus 196. So that is a change of 116. Sorry, that's 216, yeah. So 216 goes in here. Cancel, and then bring this underneath. So let's see how much steam of liquid nitrogen we make. 1.4 times 0.75 times 216 divided by 199. 1.14 kg?
1.14.
Yeah, 1.14 kg of steam is made. Yeah, whatever gains heat is at the expense of something else losing it. So you just need to know what is gaining, what is losing, and what formulas to use. Is it increasing temperature? Is it changing form? That's all.
About the gas,
Yeah, we assume that it's at the same temperature as when it went in, minus 196. Just like with water, when it's at 100 degrees as a liquid, and then it turns into steam, we say it's at 100 degrees. And then it will increase. Yes? All good? What was that, Joshua? Dude. Alright. Number 4. Can I scroll down? Yes? Do you have like a big bag of them?
no.
So you have none? That's alright, thanks. Alright, number 4. Okay, you have ice. Okay, so fusion of ice and of water and heat is supplied to concentrate. Okay, so you have a block of ice. And its mass is 0.08 kg, and its temperature is 0 Celsius, and we increase it to 20 Celsius. How much heat energy do we need to do this? So the formula is, first we change it from solid to liquid, and then we increase the temperature. So that would be 0.08 times 330 kilo times 0.08 4200 equals, so just type that all in, 330 times 10 to the power of 3 plus 4200 times 20. So I got 33120. Tannish, what's wrong? Did you have class at 9 o'clock, or is this your first class?
Yeah, no, 9 o'clock. Yeah.
What did you have at 9 o'clock?
JB.
With who?
JB.
All right. It must have been one heck of a class. All right. Okay, that's part A. Part B is the graph. So for the graph, here is time, and here is temperature. And this is in Celsius, and this is in seconds. And at the beginning it's at 0. And then the temperature doesn't change for some time until it becomes liquid, and then it increases. So that's what the graph looks like. Okay? Right.
Do you have to label? No.
I suppose I should really mark in here, this is when it's melting. Well, from here to here.
You don't need to put any numbers. Like 0.
Oh no!
We can put 0 and 20.
Well, I suppose we can at least put 0 and 20, yes. And later we can maybe put the time. The efficiency is 40%, and the power, what's the power? Does it not say?
No, that's energy. We have to compare energy output or energy.
Oh, sorry, they don't want the power, they want how much energy. Yeah. So, we can use the formula efficiency equals energy out over energy in. So we have 40% equals energy out, which is the work you want to do, which is 33120, and then what we'd like to know is what's the energy in, so that's what we want to work out. 33120 divided by so I got 82800 joules from the heater. Yeah? Did you get that too?
Yes.
Yeah?
I did the cross multiplying.
Okay. Right, 5 now. What is specific latent heat diffusion? What's the definition there? What's the definition? Energy required to
Raise one from the ground.
not raise,
Change one.
change
Substance from solid.
from solid to liquid. Yeah. Without changing its temperature. That's absolutely vital. You need to write that to get the mark in the exam. Okay? It must be absolutely change of form and not change of temperature. So do not forget to write at the end without changing its temperature. Okay? Right, let's have a look now at the B part. So part B, a plastic cup of heat contains 200 grams of water at 26 Celsius. Ice is put into the cup and the final temperature is that. What was the mass of the ice? So you have a cup of water, you put in some ice, you change its temperature, what's the mass of the ice? Now, does it say the ice is at 0? Yeah, good. Okay. So 5B, we have our cup, and we have 0.2 kilograms of water at 26 Celsius, but then it drops to 18.5 Celsius. So the change in temperature there is 7.5. Is it 7.5?
7.5. Yeah, it is.
7.5. Yeah, 7.5 Celsius. Okay, and then we have our ice cube, which we put in. So what happens with the ice cube? Well, it's at 0 degrees and then it increases to 18.5 degrees. So the change of temperature here is 18.5. Right, what is gain in energy here and what is losing? So firstly, what's gain in energy? The ice cube. So the gain by the ice cube will equal, what's losing energy? The water, isn't it? Okay, so we have here, this will be MC delta T. Now the ice, we have to be careful here. First it must go from solid to liquid, so that's ml, which is 336 kilo.
Why did they give different L in different questions?
Yeah, I'm not sure. They really should keep it the same each time. But this could, I think the reason for this is it should really be at the formula book as a list of constants. I don't know why they do this. ml plus n, and then once the ice changes into water, it increases, so that's mc delta T. Right, so we just solve this for m. We get m will equal 0.2 times 4200 times 7.5 all over 336 times 10 to the 3 plus 4200 times 18.5. If you just
0.038.
Are you sure?
Yeah, I get 0.02.
Alright, I'll type it in myself. 0.2 times 4200 times 7.5 over 336 times 10 to the power of 3 plus 4200 times 18.5. Right, what did you get, Tal?
0.02.
And what did you get, Tanish?
0.038.
0.0? No, that's it. It's 0.015,
Yeah, that's
which is the 2. Okay, so it's a 15 gram ice cube. 15 grams. Okay, that's 5 done. Now 6 and 7 left. Can I scroll down to 6? Okay, 6 now. Metal lead has a low melting point and changes from solid to liquid at 327 Celsius when a 3 kilogram mass of liquid lead was allowed to cool down, losing its heat until it was completely solid. It was found that the temperature fell from 332 down to 327. And what's the boiling point? It's 327, is it? The melting point, sorry. So here it is.
why do they see down if it's cold?
Yeah, it seems a bit odd. And what I find strange is they say has a low melting point of 327, which is a high melting point. So I think there might be a typo here. Metal lead has a high melting point and changes from solid to liquid at 327 Celsius. That sounds better. When 3 kilogram mass of liquid lead was allowed to cool down, losing heat until it was completely solid, it was found that the temperature fell from 332 to 327 in 10 seconds. So this took 10 seconds.
It fell if it's right in 10 seconds.
No, it's 332 to 327. Yes. Here it is a liquid, and here it is a solid. So it's almost like it's freezing. It turns into a solid. Well, it is that actually. Right, and then what happens later, it goes from 327 back further even to 322 Celsius in 8.4 seconds. Okay, so there's a couple of stages here. The first part is the sketch, so we'll sketch it here. So this is the time. Right, at the beginning, what's its temperature? It is 332. Then what happens to its temperature next?
It drops to 327.
No,
327.
no.
It remains the same.
It remains the same as it's melting into, as it's turning into a solid. Then it drops to 327, and then it continues to drop to 322. We don't know this time. We do know this time is 10, and then here is 18.4, but we don't know the time here, I think. They only tell us the time to go from liquid to solid, including this piece here. So I don't know this time here, but I know these two times. Okay, so that's the graph there.
When?
It says that it changed from solid to liquid at 327.
Oh, just say that?
Yeah. And no liquid to fluid. Yeah. It fell from 332 to 327.
Oh, thank you. 332, 327, and 3. What's the other number? 322. And this here is the okay. I'm sorry. So it goes like this. Then it goes like this. Then it goes like this. Okay. What times do we know? Do we know this time?
Yeah.
Yes. Okay. And then we don't know this time. Do we?
5 minutes.
5 minutes.
Yeah. Remain constant at the temperature for 5 minutes.
Ah, there it is. Yeah, sorry.
It's 310.
It was found that the temperature fell from 332 to 327 in 10 seconds, then remained constant for 5 minutes, then fell. Okay, so that's 10. So 5 minutes is 310
with the 10 seconds.
with the 10 seconds. And then this last part is
318.
318.4. Perfect. Right, that's A done. B was constant. Give the specific heat capacity of the solid lead. Okay, so the C here is 140. Calculate the rate loss of heat energy for the solid. Okay. Please, I don't want to treat you like children. I don't want to separate you. Are you making notes? Do you have this done? Joshua? Did you do all these questions?
Yeah, but I need it for.
So, where's your pen to make notes? No, actually, you know what? Sit up the front, Joshua.
No.
Joshua, get up the front. Tal, I'll move you as well, okay? Joshua, come on, hurry up. Over at the end there. Alright. So the next part here is wants you to calculate the rate of loss of heat. So they want to know how much energy do you have per second, okay? So what we need to do is work out the total energy, and then we can divide it by the time. Or, another way to think about it is because they say it's constant, maybe we can just look at a part of the process. So which piece of information do they give you? They give you the specific heat capacity of solid is 140. So I think here is liquid, here it is changing, what am I doing? Changing, and then here is solid. Yeah, it starts off as a liquid, doesn't it say that?
So it says the from solid to liquid. From solid to liquid at 327. So it's from solid to liquid.
Alright, I'll just accept that. Solid, changing, liquid. No, but that doesn't feel right, because lead is solid at room temperature, right? If you have a piece of lead at room temperature, is it solid, liquid, or gas? Solid. Right? So I would really hope that it should be this way around. Because when it gets to room temperature, it should still be a solid. Right? What do we think? Maybe. Well, I don't think it matters too much. I'll just go with it like this. Okay. Right, so what do they tell us? They tell us the specific heat capacity when it is a solid. So let's work out how much heat energy is for this part. So what formula do I use? For part B, delta Q equals mc delta T. For this part here, what's the M? What's the M? 3. The C, 140. And the delta T, 5. So this equals 3 times 140 times 5, which equals 2100 joules. Now, what's the time here? What's the time? It is 8.4 seconds, yes? So if I divide by 8.4, that means we get 250 joules per second of heat loss. That's what they're looking for.
Oh, this is the rate.
This is the rate, yes. Because remember what the word rate means. Rate always means the change over the time. So it's this divided by the time. That's the rate. Yep. Okay, now the C part is calculate the specific latent heat of fusion of the lead. So if I go back to the graph, the specific latent heat of fusion, in other words, they would like to know how much energy do you require to change it from a liquid to a solid. So 1 kilogram. How much do we have here? 3 kilograms. So if I work out how much energy was used for this part of the process and divide it by 3, I get the answer for 1 kilogram. Now, what's the rate? It is 250 joules per second. How many seconds are here? 300. So 300 multiplied by 250 divided by 3 is 25,000, isn't it? I'll write it down, sorry. It is 300 times 250 divided by 3. That would be the answer. So that's 25000. The latent heat of fusion. In other words, how much energy to change its form. Yeah?
I don't understand what the weight is.
Okay. We know from the previous part how much heat is lost per second. 250.
But those are different processes.
But the question says you can assume that the rate of loss of heat for the whole process is constant.
Okay.
Without that information you couldn't do it.
How would we do it?
They need to give you something else then. Yeah. So the answer is the latent heat would be 25 kilo. What's the formula? L equals M. Sorry. Q equals M L. So the L is joules per kilogram, isn't it? Kilo joules per kilogram is the unit. Yeah.
Work on 300 by 250.
Joules per kilogram. What's wrong, Joshua?
The top
Yeah.
300 by 250.
Yeah.
It's not formula for energy.
The 250 is from the previous one, and the 300 is the time.
No, formula for energy.
I suppose it is actually, because it's time multiplied by rate, so it would be joules in total, yeah.
Joules over seconds multiplied by seconds. So it's just joules. I know what
You want the unit, is it? Yeah, this.
That's right.
Okay, well I'll just write them in. This here is seconds. This one here is joules per second. This one here is kilograms. So it would be joules per kilogram, which is what I have here. Okay. And now the last part, so that's C. So now D is the specific heat capacity of the liquid lead. So in this C here is only when it's a solid. It's going to be a different C here when it's a liquid. But we can use the same trick as before. What's the time here? 10 seconds. What's the heat loss per second? 250. So in total it's 2,500. The delta Q is 2,500. Now what's the formula for delta Q? It's MC delta T. Now we want the C, so I just divide there by M delta T. What's the mass? It's 3, and what's the change in temperature? It's 5, is it? So in total we get 167, and it's joules per kilogram Celsius per Kelvin. Is it joules per kilogram Kelvin? I think number 6 was the most difficult one there, but the thing is, that was a section A question one year. No, it was a big section A question. Not that big. I'd say it probably would be an 8-mark question. The average number of marks for a section A question is 5 marks. So it's almost like 2 section A questions. Yeah. Okay, last one now, 7. So you have some ice at 0, how much ice would you need to add to 500 grams of water at 30 in order to bring the temperature down to 10? Okay, so you have water here. The temperature goes from 30 down to 10. How much water do I have? I have 500 grams. And the question is, how much ice would I need to add to do this? Ice at 0 degrees. So, what's losing, what's gaining? So here, I'll just say it's M of ice. What's losing here?
What's the ice?
The ice is losing, no, sorry. Ice is gaining, so delta Q gain of the ice, that must equal the loss for the water. So the heat that is the ice gets from the water when it goes in. So here we have ml plus mc delta T like before, and here we have mc delta T. The m we don't know, the L 330 kilo, the m we don't know, the C 4200, the delta T 10 in this one for the ice going to 10. It's the other one that's 20. 0.5, 4200 and 20. Because the ice is changing from solid to liquid and then increasing in temperature. The ice is added to the water. The energy the ice gets, it comes from the water. So the ice needs to first change and then increase in temperature. Okay, so M would equal 0.5 times 4200 times 20 over 330 10 to the 3 plus 4200.
0.11.
Now, don't take it personally, Tanish, but I'll just double check that. What you got?
0.11.
Yeah, I got 0.1256.
Something wrong.
In mine or his?
In yours.
I don't know, is everything I wrote there right? 0.5...
Yeah, I did it.
Oh, sorry, my bad. I'm missing a 0. 42000. Yeah, your story checks out, Tanish. It is 0.1129 about, roughly. So, in other words, about 113 grams of ice is what you need to do this job. Okay. Perfect. So what we'll do now is we'll work on the lab report. So just listen, you all have your laptops, okay? So pretty much the way we'll do it is I'd like to have a quick look at everybody, so I'll walk around, have a quick look, and then I'll give you some suggestions on things you can do. Alright? If you don't have your laptop, or if you don't have the lab report, you should really be doing something now, because it's due on Monday and today is Thursday, and then there'll be another one, and another one, and another one, and then there'll be the maths project, okay? So you don't make more work for yourself later. You have something handwritten, don't you? You have it typed?
Yes.
So you got your laptop?
Yes.
You do. Go get, no, go get it yourself now. Alright.